Welcome back to your Statistical Methods class. My name is Jacqueline Lechuga and I'm going to be your instructor for today. As always, we'll begin by reviewing some of the material that was covered on the last lecture. In the last lecture, we saw how we can use a scatter plot to show a group's scores on two different variables. As an example, we use this data, which shows a typical sleep time in grades of 5 students. Sleep time is the X variable, and grades are the Y variable. This scatter plot shows the same information. Each student is represented by a point. The coordinates of a point show the student's score on X and Y. During last lecture, we also learned how we can use the same scatter plot to show the group's Z-score on the two different variables. Here is the same scatter plot. We hide the labels for the two variables so we have more room. And we add scales to show the values of C of X and C of Y. Each point already has raw coordinates that show its X and Y coordinates. For each point, we can add standardized coordinates. The standardized coordinates are Z-scores, the C of X, and the C of Y. Now each point has two names. The first name is the point's raw coordinates. The second name is the point's standardized coordinates. This is what we call a hybrid scatter plot. A hybrid scatter plot includes points' raw coordinates and their standardized coordinates. In the last lecture, we saw that we can also calculate a point's raw coordinates and standardized coordinates without a scatter plot. We just need to calculate the Z-scores of X and the Z-scores of Y. For a particular individual, the raw coordinates are equal to X and Y. The standardized coordinates for that same individual are equal to C of X and C of Y. So the raw coordinates are the individual's values on X and Y. The standardized coordinates are the individual's values on C of X and C of Y. But there's a small complication here. The raw coordinates have a second name. They are also called the unstandardized coordinates. So we can also say that the unstandardized coordinates are equal to the individual's values on X and Y. In the last lecture, we learned that on a hybrid scatter plot, every line has two equations, the unstandardized equation and the standardized equation. To calculate the unstandardized equation, we use the unstandardized or raw coordinates of the 2 points. We use those coordinates to find the line slope and intercept. The unstandardized equation of a line includes the line's unstandardized slope and its unstandardized intercept. To calculate the standardized equation, we use the standardized coordinates of Z-scores of the 2 points. We use these coordinates to find the line slope and intercept. The standardized equation of a line includes the line's standardized slope. There is also a standardized intercept, but we will talk about that later. In the last lecture, we also talked about the most important point on a hybrid scatter plot, the point of averages. On a scatter plot, we can find the point of averages by drawing a vertical line at the mean of X and a similar horizontal line at the mean of Y. The place where these two lines meet is the point of averages. The standardized coordinates of the point of averages are always 0, 0. Its unstandardized coordinates are always equal to the mean of X and the mean of Y. In this particular scatter plot, the mean of X is 420 and the mean of Y is 75. So the unstandardized coordinates of the point of averages are 420 and 75. The point of averages is always at the center of the points in a scatter plot, as you can see in here. The point of averages is like the queen bee of the scatter plot. All the other points are like bees swarming around her. In the last lecture, we also learned that the two lines passing through the point of averages are actually a second set of axes, the C of Y axis and the C of Y axis. This is the C of X axis, and this is the C of Y axis. These two axes meet at the point of averages. The point of averages is the origin of the two axes. That is, at the point of averages, the c of x is 0 and the c of y is also 0. And as a demonstration, I did something we don't usually do, even though there is nothing wrong with it. We can hide the unstandardized coordinates of the points, so only the standardized coordinates are visible. We can also hide the x and y axes. And we can shrink the numbers for those scales of c of x and c of y. We're just shrinking them so they'll fit when we do the next thing. Then we move these numbers in, so they're closer to their axis. And we do this just as a demonstration that these lines really are axes. We can find the standardized coordinates of any point in the scatter plot just by looking at the numbers on the axes. We're now ready to begin the material for this lecture. If you had any questions about the material that was covered in last lecture, make sure you email your instructor or your TA and ask those questions. First, let's talk about two lines on a hybrid scatter plot, the positive c equal line and the negative c equal line. This is the same scatter plot we were looking at just seconds ago, showing the c of x and c of y axes. Now, normally, we don't just show these two axes by themselves. Instead, we normally show the c of x axis and c of y axis as part of a hybrid scatter plot. So let's move everything back to where it was before. We will move the numbers of the c of y axis back to where they usually are in a hybrid scatter plot, and the numbers for the c of x axis back where they usually are. And we'll make them bigger so they're easier to read. We will also make the x and y axes visible again. And we will make the unstandardized coordinates visible again. So now we're back to where we started, with the regular hybrid scatter plot. To give ourselves more space, we could hide the point of averages and c-axis. But for the lesson I'm about to show you, let's leave the point of averages and the two c-axes. Here is what I want to show you. These two lines also pass through the point of averages. And to make things clearer, I'm going to hide the points for a minute. And I'm also going to hide the c of x and c of y axes so that we can really concentrate on these two lines. This line is called the positive c equal line. And this line is called the negative c equal line. First, let's talk about the positive c equal line. The standardized coordinates of every point on the line fit this equation. C of y is equal to c of x. Put another way, c of x and c of y are the same. For example, here is a point on the line. You can see that the coordinate for c of x is 1, and similarly, the coordinate for c of y is 1. Here's another point on the line. The coordinate for c of x is 0.5. And the coordinate for c of y is also 0.5. The point of averages is on the line because its standardized coordinates are 0 and 0. Here is another point with coordinates negative 0.5 and negative 0.5. And another point with coordinates negative 1 and negative 1. I could go on forever, but you get the point. For every point on this line, its coordinate for c of x is equal to its coordinate for c of y. That's why it's called the c equal line. So now let's talk about the negative c equal line. For every point on this line, the value of c of y is equal to the value of c of x multiplied by negative 1. We write this as the c of y equals the negative of the c of x. Here's a point on the line. Its standardized coordinates are negative 1 and positive 1. The coordinates are the same, except their signs are the opposite. The sign of the first coordinate is negative, and the sign of the second coordinate is positive. Here's another point. Its coordinates are negative 0.5 and 0.5. If you multiply the first coordinate by -1, you get the second coordinate. The point of averages is on the line. The first coordinate is 0. If you multiply 0 by -1, you get 0, which is the second coordinate. Here's another point on the line, 0.5 and -0.5. If you multiply the first coordinate by -1, you get the second coordinate. The coordinates are the same except their signs are opposite. And here's another point, 1 and -1. Again, if you multiply the first coordinate by -1, you get the second coordinate. You get the idea. For every point in this line, if you get the first coordinate and multiply it by -1, you get the second standardized coordinate. C of y is equal to C of x times -1. We're now ready to go on to the main topic of this lecture and the next lecture, the correlation coefficient. The correlation coefficient is so important to statistics that it has its own symbol. The letter R is the symbol for the correlation coefficient. It's also sometimes called Pearson's R because it was discovered by a very famous statistician named Karl Pearson. The correlation coefficient is a number that tells us how strong is the relationship between two continuous variables. You remember from earlier in the semester, continuous variables are numerical variables such as height, weight, and age. You can see the word relation is hidden inside the name of the correlation coefficient. This is a reminder that the correlation coefficient is about the relationship between two variables. When we calculate the correlation coefficient for data, we will usually make a scatter plot too. The correlation coefficient and the scatter plot work together as partners. Together, they can help us understand the relationship between two variables. To show this, we will use an example involving the relationship of cigarette smoking to lung cancer. This Excel worksheet shows the rate of cigarette smoking and the lung cancer rate for each American state in 1960. The first state in this worksheet is Alabama, abbreviated as AL. The second state is Arizona, abbreviated as AC, and so on down the sheet. Each row in the worksheet represents a different state. This is just the top part of the worksheet. The rest of the states are further down in the worksheet, and so you can see them here. Column B is the worksheet is the variable sig. This variable represents the number of cigarettes sold in each state. I'm not sure, but I think the variable represents the average number of cigarettes sold per month, per adult in each state. As you can see, the average number of cigarettes sold was 18.20 in Alabama, 25.82 in Arizona, and so on down the column. Column C shows the rate of lung cancer deaths per year for each state. The lung cancer rate in Alabama was 17.5, the rate in Arizona was 19.80, and so on. We're going to make a scatter plot of this data. Here's the scatter plot. Each point in the scatter plot represents a state. The x-coordinate of this point is the number of cigarettes sold, and the y-coordinate is the lung cancer death rate. According to this scatter plot, what is the relationship between cigarette sales and the lung cancer rate? Go ahead and pause the video, take a couple of seconds to try to understand what's going on in this scatter plot. A higher rate of cigarette smoking is generally related to a higher rate of lung cancer. It's just a general relationship, and there are some exceptions. We do have some states that have a fairly high rate of cigarette smoking, but not a high rate of lung cancer. Now, according to the scatter plot, what is the relationship between a low rate of cigarette smoking and the cancer rate? Again, go ahead and take a couple of seconds and try to understand this relationship. A low rate of cigarette smoking is generally related to a low rate of lung cancer. So what we see here is a pretty clear relationship between cigarette smoking and lung cancer. We can draw a line through the points on the graph to show their general trend. The points tend to go up from left to right, and the line shows this. The points don't exactly fit on the line, but there is a general tendency. The correlation coefficient for this data is equal to 0.70. As I said earlier, R is the symbol for the correlation coefficient. This number tells us how strong the relationship is between cigarette smoking and lung cancer rates. A correlation of 0.70 indicates there is a pretty strong relationship between the two. So as I said, the correlation coefficient and scatter plot are partners. They work together and help us understand the relationship between the two variables. So now let's talk more about correlations and correlation coefficients. Correlations, that is, correlation coefficients, always lie between -1 and +1. They can be positive or negative. Let's start by talking about positive correlations. A moment ago, we saw the scatter plot of cigarette sales in lung cancer. We saw that we could draw a line through the data points that show their general trend. If this line goes up from left to right, the correlation is positive. In R, the correlation coefficient is also positive. That is, R is greater than 0. So we can see the line we drew through the points showing their general trend. This line goes up from left to right, so that tells us that the points have a positive correlation. This line is actually the positive C equal line that we discussed earlier in this lecture. Positive correlations always lie between 0 and +1, so they are always positive and they are always between 0 and 1. If R is positive and R is close to 1, we say there is a strong positive relationship between X and Y. And most points on the scatter plot are close to the positive C equal line. On the other hand, if R is positive and R is close to 0, we say there is a weak positive relationship between X and Y. And most points on the scatter plot are distant from the positive C equal line. Let me show you what I mean. In this scatter plot, the correlation between X and Y is 0.00. The points in the scatter plot are not close to the C equal line. The relationship between X and Y is so extremely weak, it's actually non-existent. In this scatter plot, the correlation is 0.50. Notice that the point in the scatter plot have moved closer to the line. The relationship between X and Y is stronger in the scatter plot than when the correlation was 0. In this scatter plot, the correlation is 0.80. The dots are much closer to the line. We say the relationship of X and Y is getting very strong. Here's the correlation of 0.95. The dots are really hugging the line. The relationship of X and Y is very, very strong. And here is the correlation of 1.0. The dots all fall right on top of the positive C equal line. When the correlation equals 1, we say there is a perfect positive relationship between X and Y. In fact, if we know the value of C of X, we automatically know the value of C of Y. Let me show you what I mean. In this scatter plot, the correlation is 1.0. X and Y have a perfect positive relationship. Along the bottom and side of the scatter plot are the values of C of X and C of Y. Suppose we know that this person has a C score of 2 on X, that is, the C of X equals 2. This must be the point that represents that person, because C of X equals 2. And we can see this person's C of Y score must also be 2. Or suppose we know that another person has a C of X score of -1. We can see which dot represents the person. And we can see their C of Y score must also be -1. For every point in this scatter plot, the C of X equals the C of Y. That is, if we know a person's C score on X, then their C score on Y must be exactly the same. Why do you think this is happening? When the correlation is +1, the points in the scatter plot get so close to the positive C equal line that they are actually lying on top of it. As we saw earlier, if a point is on the positive C equal line, then the C of X is always equal to the C of Y. Because all the points lie on top of this line when the correlation is +1, then for all of these points, the C of X must be equal to the C of Y. If the correlation is 0.50, 0.80, or any other positive value that is less than 1, we say that there is an imperfect positive relationship between x and y. And if r equals 0, we say that there is no relationship between x and y. So, to sum up, if the correlation is 1, we say that there is a perfect relationship between x and y. If the correlation is 0, we say that there is no relationship. And if the correlation lies anywhere between 0 and 1, we say that there is an imperfect relationship. But what about the correlations over here, on the negative side of 0? It's time for us to talk about the negative correlations. Here's a scatter plot of a negative correlation. The correlation is negative 0.80. You can see the line that shows the trend of the data. If the line through the data goes down from left to right, the correlation is negative. And r is negative, that is, r is less than 0. So, in this scatter plot, the line goes down from left to right. And that tells us that the correlation between x and y is negative. And we can see that r is less than 0, r is negative 0.80. And as you probably already guessed, the line showing the trend of the data is the negative c equal line. Negative correlations always lie between negative 1 and 0. If r is negative and is close to negative 1, we say that there is a strong negative relationship between x and y. And most points on the scatter plot are close to the negative c equal line. On the other hand, if r is negative and r is close to 0, we say that there is a weak negative relationship between x and y. And most points on the scatter plot are distant from the negative c equal line. Let me show you what I mean. In this scatter plot, the correlation between x and y is 0.00. The relationship between x and y is so extremely weak it's non-existent. In this scatter plot, the correlation is negative 50. Notice that the points in the scatter plot have moved closer to the line. The relationship between x and y is stronger in this scatter plot than when the correlation was 0. In this scatter plot, the correlation is negative 0.80. The dots are even closer to the line. The relationship of x and y is getting very strong. Here the correlation is negative 0.95. The dots are really hugging the line. The relationship between x and y is very, very strong. And here the correlation is negative 1.0. The dots fall right on top of the negative c equal line. For comparison, the correlation here is positive 1. As you can see, the correlation of negative 1 and a correlation of positive 1 look very similar. The only difference is that the dots go down when the correlation is negative and they go up when the correlation is positive. When the correlation equals negative 1, we say that there is a perfect negative relationship between x and y. If we know the value of c of x, we automatically know the value of c of y. We saw the same thing when the correlation was 1. In this scatter plot, the correlation is negative 1. X and y have a perfect negative relationship. Along the bottom and sides are the values of c of x and c of y. Suppose that the c of x for a particular person equals negative 2. We can see that their c of y score must equal positive 2. Or suppose we know that another person has a c of x score of positive 1. We can see their c of y score must also be negative 1. For all the dots here, there is a pattern. If we know a dot's z-score on x, then we know their z-score on y must be exactly the same number, but multiplied by negative 1. You probably see why. When the correlation is negative 1, the points are lying right on top of the negative c equal line. And for every point on the negative c equal line, the c of y is always equal to the c of x multiplied by negative 1. If the correlation is negative 0.50, negative 0.80, or any other negative value other than negative 1, we say that there is an imperfect negative relationship between x and y. So now let's review the main points so far. Correlations are always between negative 1 and positive 1. A correlation of 0 indicates no relationship between x and y. A correlation of -1 indicates a perfect negative relationship. A negative correlation between 0 and 1 indicates an imperfect negative relationship. Negative correlations closer to -1 are stronger. Negative correlations closer to 0 are weaker. A correlation of +1 indicates a perfect positive relationship. A positive correlation between 0 and 1 indicates an imperfect positive relationship. Positive correlations closer to +1 are stronger. Positive correlations closer to 0 are weaker. So overall, correlations close to 0 in the middle are weaker. Correlations close to -1 on the left end and correlations closer to +1 on the right end are stronger. So let's talk a little bit about the strength of correlations. The strength of a correlation has nothing to do with whether the correlation is positive or negative. Instead, the strength of a correlation depends on how close the relationship is to +1 or -1. A correlation of 0.80 and a correlation of -0.80 are both equally strong. Both correlations indicate there is a very strong relationship between x and y. Here's a correlation of 0.80. The points are getting pretty close to the positive c equal line. Here's a correlation of -80. The points are also pretty close to the negative c equal line. A correlation of +80 and a correlation of -80 are both equally strong. Similarly, a correlation of 0.50 and a correlation of -0.50 are both equally strong. Both of them indicate there is a strong relationship between x and y, though not as strong as 0.80. Here's a correlation of 0.50. The points are fairly close to the positive c equal line. Here's a correlation of -50. The points are fairly close to the negative c equal line. When statisticians interpret correlation coefficients, here are some of the terms they often use. A correlation of 1 or -1 is perfect. A correlation around 0.80 or -0.80 is very strong. A correlation around 0.50 or -0.50 is strong. A correlation around 0.30 or -0.30 is moderate. Correlation around 0.10 or -0.10 is small or weak, and a correlation of 0 means there is no relationship. Let's talk about one more difference between positive and negative correlations. We will start with positive correlations. We will use the scatter plot as an example. It shows a positive correlation. Let's focus for a minute on these individuals up here in the top right corner. These individuals lie toward the right side of the graph, indicating they have a high score on x. They also lie towards the top side of the graph, indicating they have a high score on y. When x and y are positively correlated, there are a lot of people in this upper right corner because people high on x also tend to be high on y. There are also a lot of people in this lower left corner. These have low scores on x and low scores on y. When x and y are positively correlated, people low on x tend to be low on y. So to sum up, if the correlation is positive, people with high scores on x tend to have high scores on y. And people with low scores on x tend to have low scores on y. Now let's talk about negative correlations. As an example, we will use this scatter plot which shows a negative correlation. When the correlation is negative, there are a lot of people in this lower right corner. They have high scores on x, but low scores on y. When x and y are negatively correlated, people high on x tend to be low on y. There are also a lot of people in this upper left corner. These people have low scores on x and high scores on y. When x and y are negatively correlated, people low on x tend to be high on y. So to sum up, if the correlation is negative, people with high scores on x tend to have low scores on y. And people with low scores on x tend to have high scores on y. In the final part of today's class, I will explain how to calculate R. The calculations for the correlation coefficient can be summed up in one sentence. R is the mean cross product of the z-scores. I'm going to explain what a cross product is and show you how the calculations are made. And I'm going to have you do the calculations along with me. So if you haven't already looked at the class exercise on your folder, please make sure you first locate that file. This is your class exercise. It has data for 5 individuals, showing their scores on 2 variables that we will call x and y. The first individual has a score of 4 on variable x and a score of 12 on variable y. The second individual has a score of 8 on variable x and a score of 6 on variable y, and so on. This is the way data sheets are set up in Excel or SPSS. Each row represents a different individual. This is a scatter plot showing these 5 individuals. The first person on the handout has a score of 4 on variable x and a score of 12 on variable y. Try to locate this person on the scatter plot. Okay, now looking at this scatter plot, are x and y positively correlated or are they negatively correlated? They are positively correlated, and how do we know that? Well, because the line is going up from left to right. And what is the name of this red line in here? It's called the positive z-equal line. To get the correlation coefficient, we first have to transform the raw scores for x and y into z-scores. By now, you know how to calculate the z-scores, so go ahead and calculate the z-scores. It's probably easier if you first calculate the z-scores for x, then go back and calculate the z-scores for y. Okay, here are the z-scores. If you got other numbers for the z-scores, you should go back later and find out where the calculations are wrong. But for right now, I want to show you the next step for calculating the correlation coefficient. This next step is to calculate the cross products of the z-scores. Although the term cross products is probably new for you, the idea is actually very simple. To find the cross product of these two z-scores, we simply multiply them together. Let's start with the two z-scores in the top row. The z-score for x is negative 1.5 and the z-score for z is negative 0.5. To get their cross product, we simply multiply these two numbers together. Remember that when we multiply a negative times a negative, we get a positive. Negative 1.5 times negative 0.5 is positive 0.75. Positive 0.75 is the cross product of these two z-scores. So we write positive 0.75 in the column for cross products. We do the same thing for this second individual. We're going to be multiplying negative 0.5 times negative 1.5. Remember that negative times a negative is going to result in a positive number, which in this case was 0.75. Go ahead and calculate the very last cross products. Here are the 3 cross products, 0, 0, and 2.25. As you remember, this is the one-sentence description of how to calculate the correlation coefficient. R is equal to the mean cross product of the z-scores. To find R, all we have to do is calculate the mean of these 5 cross products. So go ahead and calculate the sum of these 5 numbers and their mean. When we add together the 5 cross products, their sum is 3.75. To find the mean, we divide the sum by 5. And here is the mean. That is the mean of the cross products. In this mean, the mean of the cross products is R. So R is equal to 0.75. Here's a definition of R. R equals the mean cross product of the z-scores. You should memorize this definition because it will help you remember how to calculate R. First, you transform the raw scores into z-scores. Second, you cross-multiply the z-scores to get their cross products. Third, you calculate the average of the cross products to get R. Today you have learned a lot about the correlation coefficient. You have learned how to interpret correlations and how to calculate them. In the next lecture, we'll continue learning about correlations. See you next time.